Hello everyone, and welcome to our sixth lecture. So this lecture is going to change gears a little bit. So far, we've been focusing mainly on structure, structure of the neurons, structure of the brain, and we're going to start talking about function. And we're not going to quite get there in this lecture. This is more background, more of a refresher, because you're going to need to understand a little bit about chemistry to understand how neurons work. So this lecture, if you notice, doesn't have as many slides in it, and it's going to be a little bit shorter, and that's on purpose, because this is a content area that maybe you haven't seen in a while. We're going to be talking about atoms and ions and electric charge. So especially if it's been a while since you had chemistry, and for many of you it probably is, you may need to go back and review some of this. You may need to watch parts of it again. And that's okay. So I'm going to keep this one a little bit shorter, and we're going to go over some chemistry, and we're going to go over how ions work. And today's topic is ions and ion channels, which, as we'll see, are parts of a neuron that interact with ions. So we're learning about ions and ion channels, and first we're going to start real basic and define what ions are. And we're also going to focus on a couple, so we're not going to do the whole periodic table. We're only really going to worry today and next time about two kinds of atoms. That's sodium and potassium. There are some others that we'll focus on when we get to synaptic transmission, but for right now, there are really just two, so don't worry about it. And we'll see that ions have rules that they have to follow. So they don't have free will, they don't make decisions. But they do move around. They have sort of a behavior. But we understand that behavior. Ions are pretty simple. And so we'll look at forces that affect ions. And then we'll look back at the neuron and see, what do ions have to do with the neuron? What interacts with ions? So more specifically, we're going to understand what ions do, how they behave. Because again, there are rules they have to follow. If you understand those rules, then you can understand how neurons use electrical signaling. And that is the end goal of this unit on ions and ion channels and action potentials. We know that neurons use electrical signaling, but what does that mean? And how does it work? So that's where the behavior of ions comes in. And we'll also see what ions have to do with neural function. So neural function, neural activity, consists of electrical current. And electrical current, electrical signaling, means that ions are moving around. And so instead of just using sort of the blanket phrase, electrical signaling, which may be a bit vague, we're going to talk about ions and what those ions are doing and why that comprises electrical current, electrical signaling. And again, the parts of a neuron that work with ions are called ion channels. So we're going to see how those work. They're like little machines. And so we'll look at these little machines and see what they do and try to understand why they do what they do. And this is all going to get us ready for next time, where we'll talk about action potentials. And action potentials are the electrical signals that neurons send. So we talked about the parts of a neuron, the dendrites, the axon, and an action potential is the electrical signal that goes from the end of the cell body down the axon to the axon terminals. So we're going to get ready to learn about that process. We're not going to cover it here, but we need our background in ions and ion channels. That's going to set us up to learn about action potentials. So neurons use electrical signals. We've already said that, but again, we're going to get more specific starting about now. So a little bit of history. We've already talked about Galvani in the 18th and early 19th century. And Galvani discovered that electricity has something to do with the nervous system, with how our bodies work. He thought it was sort of a life force. And that's, again, a bit vague, a bit mystical, but there's a kernel of truth to it. Electricity is important. We remember his experiment, making those frog legs move by stimulating the frog's body electrically. And it wasn't that the frog was deciding to move. Half the frog was missing. So it was just that electricity caused these legs to move. And that's still largely true. So here's a quote from a more recent source saying the agent that operates our nerves and muscles is electricity. So that part Galvani had right, and that was a long time ago, and that hasn't changed. So our understanding of electricity has improved. It's not a life force. It is the movement of charge. But the Galvani's principle still holds. So again, to understand what this unit is about, we have to do a quick refresher on chemistry. And again, for some of you, it may have been a while. That is okay. So if you remember chemistry, we have here a sort of abbreviated version of the periodic table. And even this is not a list of elements that you need to remember. We're only going to worry about two. But if we recall, chemical elements are defined by the number of protons they have. So hydrogen has 1 proton. Helium has 2 protons. That's what makes them hydrogen and helium. And protons have a positive charge. So if you add protons, it'll become a different element. If you take away protons, it will be a different element. So for a given element, the number of protons is constant. And today we're going to really worry about sodium and potassium. So sodium, as we can tell from this table, again, you don't need to know this, but sodium has 11 protons. That's what defines it. Potassium has 19 protons, so a few more. And again, those numbers aren't important, but we can't change the number of protons without changing what the element is. So if it's sodium, you know it has 11 protons. If it's potassium, you know it has 19. What can change is the number of electrons. So you can change the number of electrons that a sodium atom has, and it's still sodium. So an ion is any atom where those numbers aren't equal. If there are more protons than electrons, or fewer protons than electrons, that's what makes it an ion. It has a charge, because electrons have charge, and protons have charge. And if those numbers are equal, then the charge evens out. If they aren't equal, then you've got an ion because you've got some amount of charge carried by that atom. So it has an uneven number of electrons and protons. It carries a net electrical charge. In the case of sodium and potassium, they have a net charge of +1. They have, when they're ions, their most common ionic form is that they have 1 fewer electron than they have protons. So they're a little unbalanced. They have a net positive charge. And this is a diagram from your book. And we see a little table up top that lists some common ions that have to do with neurons. And we also see on the far right sort of the vague category of proteins, which we're not going to worry about, really. So ions in any atom will have a concentration. That means how much of that item is there in a given volume. So the number, you don't need to memorize the numbers, but we just compare these numbers. So we have a neuron, so there's a space outside the neuron, there's a space inside the neuron, and how much sodium you find outside and inside is different. So if we compare the numbers, we can see there's a lot more sodium outside the neuron than there is inside, and that's important. So we can compare these two numbers, we compare the concentrations, and see that there is a bigger concentration of sodium outside than inside. Incidentally, sodium is abbreviated Na for historical reasons. The Na means sodium. And potassium is symbolized by K, so unfortunately, neither symbol starts with the same letter as the word itself. So that's unfortunate, but that's the way it is. So potassium, abbreviated K, has the opposite story of sodium. There's a lot more inside than there is outside. If you compare these two numbers, there's very little potassium outside the neuron, but there's a lot of it inside. And so we have different concentrations of sodium and potassium, depending on whether we're looking outside or inside the neuron. You can compare other two ions on this table, chloride, which isn't important for this lecture and next one, and then calcium, which isn't important for this lecture or next one, but they will be important for our upcoming unit on synaptic transmission. So we'll start with sodium and potassium here. When we talk about signaling between neurons, so chloride and calcium will become very important. For right now, we're just talking about signaling within a neuron, getting from one end of the axon to the axon terminals. And for that, it's really just sodium and potassium that are important. And it's crucial to remember that sodium is highly concentrated outside, not so much inside. And potassium is highly concentrated inside, and not so much outside. So outside the neuron has a lot of sodium, inside the neuron has a lot of potassium. And just remember that. Okay, so we have our neuron, and some terms come up pretty quickly. So one is cell membrane. So a neuron is enclosed by a cell membrane. It's a layer of fats that form the border of the neuron, but really any cell has a cell membrane. And so there's a border. And charge does not cross that border very well, very easily. And so you can have ions outside the neuron, and they have a hard time getting in. They can't get in. And you can have ions inside the membrane, inside the cell, and they can't get out. So charge and ions don't travel across that membrane. That membrane is like a wall. It's a barrier. And so it separates the outside from the inside structurally, but it also has an important consequence for ions. It forms that border that they can't cross. And that brings us to the idea of electrical potential. So electrical potential is the difference in charge between two locations. Here, we're talking about the outside and the inside of the axon, but it's measured in volts, just like you have a 9-volt battery. That 9-volt label means that the difference in charge between the two terminals of the battery is 9 volts. Here, the differences in charge are not so big. So we measure things in millivolts, thousandth of a volt. But because sodium, potassium, other ions have different concentrations inside and outside, because they also carry a charge, you add up the charges outside and you add up the charges inside, and you have a total difference in charge. You have an electrical potential. So that's what that term means. It describes a difference in charge. And unless the axon is firing an action potential, that difference is pretty constant for an axon. And we can measure that difference with what's called an electrode. So this is an instrument. It's a very thin wire or tube that you can insert into the membrane. You can put it inside the cell membrane, inside the axon. And so you can measure the difference between charge outside and charge inside. And we'll get more to that difference here in a little bit. But just for now, know that there on average is more positive charge outside the axon than there is inside. So you have a potential difference. So you have a difference of usually around minus 65 millivolts. And that minus sign is important. It means that the inside is more negative than the outside. The outside is more positive than the inside. That's two ways of saying the same thing. You're just talking about a relative amount of charge. So we have a difference in the total amount of charge outside versus inside. And we can measure that with an electrode. So we have ions, and now again we're speaking generally. We're not going to get to action potentials yet. But ions are charged particles. And that means they follow certain rules. They have two forces that act on them. And if you understand those two forces, then you have all the tools you need to understand how action potentials work. So the first force is called diffusion, and it's pretty simple. All it means is that ions, and really any particle, but today we care about ions, ions move from where they're concentrated to where they're not. They move from where they're really common to where they're less common. So in this diagram from your book, if you pour some particles into a tank of water, at first they're all going to be on one end, wherever you poured them in. But over time, they're going to spread out. And you can't really see ions, but if you've ever put a drop of food coloring in a glass of water, At first, the drop is localized. You can still see the drop, that one drop, and the rest of the glass is clear. But if you wait a while, that food coloring will diffuse, and pretty soon that entire glass of water has a uniform color. So that's diffusion. And if you've never done that, try it out. If you don't have food coloring, any colored liquid will work. So you can drop it in, and it will diffuse throughout the glass of water. And that's how diffusion works. Things go from where they're very concentrated, very common, to where they're less concentrated. So that's rule number one. And the difference between the concentrated region and the non-concentrated region, we refer to the difference in concentration as a concentration gradient. And all that means is there's a difference. Sort of like we have an electrical potential, we have a concentration gradient. And ions tend to move down their concentration gradient. They move from where they're common to where they're uncommon. So that's rule one. Rule two is called the electrostatic force. And this has to do with electrical charge. And the rule here is that like charges repel one another and opposite charges attract. Sort of like magnets. The equivalent poles of a magnet will repel, but opposite poles will attract one another. That's why you turn a magnet around and the two ends will come together. If you rotate one end, they'll repel. So same deal for electrical charges. So two positive charges will push each other away, and a positive and a negative charge will pull toward each other. Two negative charges, which we're not really going to deal with today or next time, but if that happens, two negative charges will also repel each other. So ions have an effect on other ions based on their charge. Well, why are we worrying about this? Because we know the membrane separates the inside from the outside, and we know that ions have different concentrations. And so we have these forces, but they sort of don't have anywhere to go because they can't cross the membrane. So why are we worried about the forces that affect ions? Well, it turns out that the membrane has these little proteins, these little machines that are built into it. And those machines, those proteins, are called ion channels. And those channels will let ions through. So there is a way to cross the membrane if there's an ion channel around and it's open. If it's closed, it's just like the rest of the membrane. Nothing you can do. Ions can't go across. If it's open, an ion can go through the membrane. There's a little gate. So this is just a diagram of what ions are made of. So this is just demonstrating their proteins. And you'll see those proteins illustrated various ways, sometimes as cylinders, sometimes as these sort of squiggly lines, sometimes as these sort of strange shapes. But however you depict them, the important thing they all have in common is they have a hole in the middle. And if the channel is open, that means ions can flow through that hole and make it from the outside to the inside, or from the inside to the outside. So this is what they look like structurally. I mean, not literally, these are cartoons, but they're made of proteins. So when we see cartoon versions of these channels, just know that they're proteins. They're little machines that live in the cell membrane. And these channels can select for particular ions. What does that mean? It means they're picky. So a particular kind of channel might only let sodium go through. A different kind of channel might only let potassium go through. So how does that work? How do they know which ion is around and only let a certain kind of ion through? So for potassium channels, or again, potassium is designated with a K, potassium channels are a certain size. And we've mentioned that sodium ions have 11 protons, potassium has 19. So technically, sodium is smaller. But that's the ion itself. For reasons we don't need to go into, effectively, sodium is bigger. It's a bigger object because sodium and potassium both attract water molecules. Those water molecules will cluster around these ions because of their charge. And so sodium is better at attracting water than potassium is. So even though sodium itself is a smaller ion, it's got this giant shell of water molecules that surrounds it. And so in effect, sodium is bigger. Potassium isn't as good at pulling in water molecules. Its shell is smaller, it's kind of thin. So a potassium ion is effectively just smaller than a sodium ion is. So a potassium channel is a certain width, the hole is a certain width, and so that hole is wide enough to let potassium ions with their surrounding waters through. But it's not big enough to let sodium ions with their water molecules through. It's sort of like a coin sorter or a sieve. The holes are only so big, and so anything smaller than that hole will go through. Anything too big for that hole can't go through. So because of these water molecules, sodium is effectively bigger, and potassium can go through, but sodium can't. Now the sodium channel is a little bit different. Sodium is bigger, so it can't use the size of the ion as its mechanism of selectivity. Any hole that's big enough to let sodium through is big enough to let potassium through. So those ion channels work a little bit differently. So here's a close-up view. At the bottom, we see part of the membrane close up. That part's not really important. It just shows you that it's a lipid molecule, a fat. But up top, we see a sodium ion, a little red circle with the plus in it. And we see these water molecules, H2O, an oxygen and two hydrogens. And they're all clustered around that sodium ion. Because the sodium ion is charged, it attracts those water molecules. So again, the sodium channel can't use size to filter out the potassiums, but the middle part of that channel is the right size to sort of strip off those waters, and it's exactly the right size for a sodium ion and exactly one water molecule. So again, potassium, the ion itself, is a little bit bigger. So if potassium loses its waters, which is what this channel does, it's not the right size. It's sort of like a lock and key. And so a sodium can fit exactly in this space and then pass on through, whereas a potassium cannot. So this sodium channel is special because it makes sodium lose its water and then has a gap that's exactly the right size for a sodium ion and exactly one water molecule. So that's how the sodium channel works. So we've talked about channels, and we're about to start talking about pumps. And there's an important difference there. A channel, we see here on the left, and a channel can open and close. Many of them have a little gate, and that's what's depicted here. You see that little gate swing open, and now ions can flow through. But channels can open and close. When they're closed, ions can't get through. When they're open, ions can get through, and as we just saw, a particular kind of ion. So the channels are picky. But the channels don't actively move anything. All they can do is open, and ions, a particular kind of ion, will flow through in whichever direction it wants. And we'll see that when we say wants, what its behavior is dictated by our two rules, diffusion and the electrostatic force. So when that gate is open, or when the channel is open, ions can flow through, and which way they flow is determined by those two rules. Then there are pumps. Pumps move ions in a particular direction. They don't care about the two rules. So this is, for example, this sodium-potassium pump, which is the only pump we care about for this unit. So it moves sodium from inside the cell to outside. It moves potassium from outside to inside. Those are not the directions that sodium and potassium want to go according to the two rules we talked about. What does that mean? Well, it means that pumps take energy. You have to feed energy, chemicals, to these pumps in order to make them work. Channels don't require any energy. When that gate opens, the ions flow through whichever way the rules say they should. That doesn't take any energy to move those ions. The pump does take energy to move the ions because it's moving them against the direction that they would otherwise go. So as we'll see, sodium, really concentrated outside, there's a positive charge outside that's going to push on sodium and make it go in. But the pump pushes sodium back out. Potassium wants to go out. The pump pushes it back in. And so that's why there are different concentrations of sodium and potassium inside and outside the cell. It's because of this pump. If you didn't have the pump, after a long, long time, sodium and potassium would equalize between the inside and the outside. But because you're using up energy and you're using this pump to keep those concentration gradients the way they are. You're keeping sodium concentrated outside, you're keeping potassium concentrated inside. So that takes the pump requires energy, and the pump moves those ions in the opposite direction that they would otherwise go. And that's important because now we have these concentration gradients. We have our rules, and those rules say that the ions will want to go in a particular direction. And they want to go in that direction pretty strongly because of these pumps, because these pumps are maintaining those concentration gradients. So this is a diagram from your book. And so here we have the sodium-potassium pump. It's pushing sodium out, it's pushing potassium in, and so sodium is going where it's already concentrated, potassium is going where it's already concentrated, so we're keeping those things kind of separated. We're keeping potassium concentrated inside and sodium concentrated outside. That's what the pump does, and again, that takes energy. Now, we've talked about ion channels, and they can open or close. There are potassium channels that are usually closed. We don't see those here. However, there are potassium channels that are always open. And so those are those little gates that you see in this diagram from your book. What does that mean? Well, it means potassium can go in and out of the cell however it wants. Sodium doesn't have that. There are no channels for sodium that are always open. So sodium is stuck outside. There are, as we'll see, sodium channels that can open, but they're not always open. And so sodium, unless those channels are open, is just stuck out there. Potassium has sort of a free pass. It can go in, it can go out, and as we've seen, that sodium-potassium pump keeps potassium in. So that gives us an equilibrium potential. When the neuron is just sitting there, there's a difference in charge between the inside and the outside. We've already seen this. In this diagram, it's negative 65 millivolts. It can vary a little bit, but we'll stick with minus 65. So what does that mean? Well, it means there's more positive charge outside than inside. There's a net difference in charge across that membrane. So why is it that way? Well, we've already seen there are differences in concentration between sodium and potassium. And at equilibrium, potassium can go in and out as it wishes, but it's concentrated inside because of the pump, and because there's a lot of positive charge outside, mainly due to sodium. And so we have our two forces. We have diffusion, and we have the electrostatic force. Diffusion wants potassium to go out. Remember, diffusion says ions move from where they're concentrated to where they're not. Well, there's a lot of potassium inside, not much outside. So diffusion says, potassium, you need to go out. You need to leave the cell. However, the electrostatic force says the opposite. There's more positive charge outside. Potassium is positive. The electrostatic force is going to push those positive potassium ions back inside the cell. So we have these two forces saying opposite things. The diffusion force pushes potassium out. The electrostatic force pushes potassium back in. So those are both happening. So potassium is going in and out across those channels that are always open. But it's doing so in equal rates. So that's why it's at equilibrium. Nothing's really changing. And it's because those two forces balance each other out for potassium. What if we change things? So normally, sodium doesn't have any way to move across the membrane, but there are sodium channels. If they open, sodium is going to flow very quickly into the cell. Why? Well, let's think about our two forces. So sodium is a positive ion. It's highly concentrated outside the neuron. Well, the diffusion force is going to push sodium inside the cell. It's going to move from where it's concentrated to where it's not. And it's not very concentrated inside. So all that sodium that's sitting there outside, if it's given a chance with an open channel, will flow very quickly inside the cell. Let's think about the electrostatic force. There's a lot of positive charge outside. Sodium is a positive ion. The electrostatic force is going to push sodium inside the cell. So those two forces are acting in the same direction for sodium. So that's a different story from what we saw for potassium. Potassium, we have the balance of forces. One pushing in, one pushing out. Sodium, we have both of them pushing inside. Sodium is just waiting for that chance to go inside the neuron. So if that channel is open, sodium is going to rush in. It's less concentrated inside the cell. There's also less positive charge inside the cell. So the positive charges that are outside are going to repel sodium ions. They're going to push sodium inside the cell. So let's say that starts happening. So sodium starts rushing in. Well, now the situation starts to change for potassium. There's still a lot of potassium inside, but now it's not quite so negative inside the cell because of all the potassium, or because of all the sodium that's come in. Remember, sodium carries a positive charge. And so when sodium rushes into the cell, the membrane potential becomes positive, gets more positive. There's more positive charge inside. So the difference decreases. Before it's at minus 65 millivolts. If more sodium comes in, it'll go up to minus 64, minus 63, because there's less and less of an imbalance. There's more positive charge inside the neuron, the more sodium comes in, and so the membrane potential changes. Well, as that difference decreases, as the membrane potential goes up, well, now potassium has less of a reason to stay inside. Before, there was all that positive charge out that was pushing potassium back in. But now positive charge is inside the cell too. So now potassium is going to flow down its concentration gradient. A little bit's going to go out to compensate for the fact that sodium is going in. So extra positive charge in the form of sodium has come into the neuron. So now some positive charge in the form of potassium is going to go out, because potassium now has sort of an incentive to leave the cell. Before, its two forces were balanced. But now there's all this sodium coming in, bringing in positive charge that's going to repel the potassium. Now, it's not a whole lot at first, so potassium just leaves a little bit at a time. But as we'll see when we get to action potentials, this happens very quickly. So that's what's happening if sodium is allowed to enter the neuron. It'll flow in very quickly because both forces point in. And then potassium is no longer in equilibrium. So it'll start to leave if you let it. And what we see here on the right of this diagram are arrows that indicate the size of the forces pushing sodium and potassium either in or out. On the right we have sodium, on the left we have potassium. So we have this big arrow on the right. So sodium has a huge total force pushing it in. Both forces acting in the same direction. As sodium flows in, potassium starts to experience a total force that's a little bit pushing it out because of the positive charge that's come in. So at first, potassium is balanced in terms of the forces. As positive charge comes in with sodium, now it starts to leave to compensate for this extra positive charge that's come in. So these ion channels, again, are normally closed. The sodium channels are a good example. Again, we have those potassium channels that are always open. We're also going to have potassium channels that are usually closed. We have two kinds of potassium channels, just one kind of sodium channel that we care about. So what does that mean, open and close? Well, as we've seen, there's a hole through the middle of that ion channel, and it can open up. So it can open or close. Normally it's closed, but it can open. And it does this a variety of ways. This diagram we're not going to belabor. But there can be a part in the middle of the channel that just changes shape a little bit, and now there's a gap, so it lets ions through. You can have the whole channel sort of twist around like the lens of a camera, like the shutter on a camera. And so everything sort of rotates a little bit, and now that gap opens and closes. You can also have an actual particle, the bottom part of this diagram. We sort of a ball and chain. So that ball can go and plug the end of that channel, so now it's closed. So those are just three ways that a channel can close. This will be more important as we progress through the course. We don't need to memorize the contents of this diagram, but just to give you a preview of what's coming, those channels can open and close for quite a few reasons. We're going to focus on one today, but again, preview here. Channels can open and close because there's a chemical out there. It could be a neurotransmitter that binds to the channel and it makes it open. It could be a change in voltage, a change in potential, and that's the case here today, that makes it open. Or something can physically pull it open. If the membrane stretches, that can pull a channel open. That'll be important for our unit on the senses. Today we're going to focus on that voltage gating, on a difference in potential causing that channel to open up. But just so you know, for the future, there are many things that can open up a channel. Depends on the kind of channel. So we're going to focus on voltage gating here. And voltage gating, a voltage gated channel, means that it is sensitive to the difference in charge across the membrane. So normally, we've already seen there's more positive charge outside than inside. So your membrane potential is a negative number, in our case minus 65 millivolts. And under that condition, the channel is closed. But as positive charge starts to move in, especially if that environment inside the neuron becomes actually more positive than the outside, then the channel can open. It senses what the voltage is across the membrane, and if it gets positive enough, if the membrane potential increases, goes up, then it can open up. And that's going to be important for action potentials because what we're going to see is that voltage across the membrane does change. And once it changes enough, that's going to open up these voltage-gated sodium channels. We're also going to see there are voltage-gated potassium channels. So when the membrane potential changes, if it changes enough, if it reaches what we call threshold, then these channels are going to open, and they're going to let their special ion flow through whichever way that ion wants to go. After a while, those channels are going to close up again, and you can't open them. That's called inactivation. So they sort of get tired. They've been open for a while because the membrane potential changed. They get tired. Now they're going to inactivate. And now you can't open them again. You just have to wait for a little while. So that process of changing the membrane potential from negative going toward positive, from minus 65 millivolts up to minus 60, up to minus 55, and so on, all the way up to positive numbers. That process is called depolarization. So just like you can have a polarized opinion, something that's really extreme, you have a polarized membrane. But as positive charge enters the neuron, that membrane potential will go up from minus 65 to minus 50 to minus 30, all the way up to positive 20, positive 40. It's not as polarized as it was, so it is depolarized. So that's what depolarized means. It means it's gone from minus 65 millivolts up. You can also have a membrane potential get hyperpolarized. It can go from minus 65 to minus 75, minus 85. So it's getting more extreme. It's hyperpolarized. You'll hear depolarized more often because that's the process that initiates an action potential. But that's called depolarization, and that's an important term. So as the membrane gets depolarized, it will open these voltage-gated channels. After they've been open for a while, they will inactivate no matter what the voltage is. And they're just going to stay closed for a while. And then they go back to their resting, their closed state. So there's a difference between inactivated and closed. Closed means if the voltage is right, it'll open. Inactivated means it was just open for a while, it's tired, it's going to be closed, and not let ions through no matter what. So we use those terms differently. Inactivated, the hole through the ion channel is closed, but specifically inactivated means nothing gets through no matter what the voltage is. Closed, or resting, means it just happens to be closed right now. It's not letting ions through, but if the voltage is right, it'll open up. So 3 different states, as we call them, that these ion channels can occupy. Closed, open, inactivated. Okay, so that will do it for our unit on ions and ion channels. Again, this unit is probably unfamiliar territory. At the very least, it's probably been a while since you thought about ions, thought about chemistry, thought about proteins. So if you need to go back and review this, feel free. And of course, do take the online quiz. So what did we just cover? Well, we talked about ions, what they are, and why they move, those two rules that govern the behavior of ions. And again, if you know those two rules and understand them, action potentials make total sense. You can predict what's going to happen at each stage of the action potential. It's no longer a process of memorization, and in fact, it shouldn't be. If you understand those two rules and you know sodium and potassium are positive and you know where they're concentrated, everything else is just a consequence. So you can deduce what an action potential is. You don't actually have to memorize a complex sequence of steps. You'll understand it better. So do understand those two rules. Do understand what ions are, and sodium and potassium in particular. We talked about ion channels and selectivity. So ion channels are proteins or little machines. Some are always open, but some are usually closed, and when they're open, only let a particular ion through. We talked about how that works. So we talked about how ions open and close and become inactivated. And those are, again, 3 different states that are important for our next unit on action potentials. So for next time, so today, or soon after watching this lecture, again, if you need to go back and watch it again, that is totally fine. Take the online quiz. It's a required part of the course, but it's also a good way of assessing your comprehension of this unit. And this is a tough unit. So before you take the quiz, again, maybe watch the lecture again, go over your notes, read the book. This is tough stuff. So do take the quiz when you're ready. And again, they are due Sunday evenings. Read chapter 3. Do the reading for next time after you've taken the quiz. So there we're going to start talking about action potentials, which are the electrical signals that travel down axons within a neuron. And as always, do the reading before lecture. It'll help a lot. Okay, that will do it for this lecture, and I will see you next time.